Well, as mentioned, we are covering probability theories and statistics analysis today. So if you were in Canvas earlier this week, you didn't see the stuff because I just finally finished this presentation last night. So we haven't covered this stuff in the systems class in a little while, but it's really important stuff. And if you've been in program management and after we go through this, you're going to be like, oh, that would have been great to know before I got in program management. Because this is information that you use very frequently in the field of safety and health, as far as like figuring out how likely is it that you're going to have incidents, what are your incident rates, kind of where do you need to focus your attention. And as we get further in the textbook for this class, there will be some of the types of analysis where some of these numbers will come back. But don't panic just from hearing the word math, probability, or statistics, because we're not going deep into this. We're not going into the realm of like having to do all different types of like special software to analyze things and stuff like that. We won't get into that here. We're just barely scratching the surface of like, you might have covered this in 4th grade math class kind of level, okay? So not terribly scary. The purpose of statistical analysis is to provide sufficient info for management to make an informed decision regarding risk, acceptance, or rejection. So far in this class, we have been talking about the risk analysis, looking at like what's the level of risk and prioritizing the things that we need to do. We've talked about identifying corrective control measures and things like that. Statistical analysis helps us to kind of back up why do they need to do these things that we're asking them to do? Besides just the moral factor of we don't want to hurt or kill people, there is the financial benefit to be gained from it. And so anytime we can back up our recommendations with actual data, numbers, return on investment, and all of that kind of stuff, we're more likely to get the attention of management because we're speaking more of that same language that they're speaking. So when we talk about statistics, kind of the absolute surface level is the difference between probability and statistics itself. Probability examines the likelihood of a specific failure event, giving a single opportunity for it to happen. And then statistics focuses on the number of times a failure event will occur given many opportunities for it to happen. And statistics is generally looking backward, where probability is looking forward. So probability, some of you, I don't know, any of you guys in the program management class right now? Now, well, yesterday I kind of subbed the first 10 minutes till a teacher showed up yesterday and they were talking about leading and lagging indicators. It's kind of the same thing that we're talking about, just in slightly different terms here, because probability would be those leading things, looking at it before it's happening, what's the chances that it's going to occur, and then statistics is after it's already occurred, going back and looking at how frequently can we anticipate that those types of things are going to happen. So through the use of basic probability theory and statistics analysis, the system safety function can actually assign expected values of certain hazards and failures to determine the likelihood of occurrence. So when you guys, you remember from last week, we talked about risk. What were the 2 things that make up risk? Oh, hit the wrong button there. Probability and remember, if an accident happens, no, the likelihood and probability are going to be kind of the same realm. What's the other side of it? How likely it is to happen and how bad will it be if it does happen? So when we're looking at trying to figure that out, we need to be able to know how likely. It's pretty easy for us to determine how bad it would be. If somebody sticks their hand in the machine and it chops off fingers, that's the expected outcome. We can kind of assign a severity level, but how do we figure out how likely or how probable is it that that is going to occur? So that's where the statistics stuff comes in important. So with probability theory, what we're looking at is predicting the occurrences of things that could happen within our working environment. This is always going to be represented numerically as a value between 0 and 1. There are no options below 0 because that would be less than a 0% chance of happening. So never going to happen. 0 is the lowest you can go. and nothing more than 100 or than 1, because 1 equals 100% chance that it's going to happen. But there is an infinite level of possibility between 0 and 1. How many numbers come between 0 and 1? Anything with a point, anything. It can be infinite number. It could be like this example, 0.5. It could be 0, 1, 2, 3, 4, etc. Okay, so there is an infinite number of possibilities that could be between those. The probability of something that is 0.5 has an equal chance of not happening or actually happening. So that's like a 50% chance. It could go one way or the other. So kind of a visual representation when we're thinking about probability, we look at the little spinners over here on this side. What's the probability of the spinner landing on blue right here? 0 chance. There are no blue, so it would be impossible for us to hit that. And of course, if it was exactly the opposite and every one of those was blue, then our chance would be what? 100% chance that it's going to land on blue. But if we have anything less than 0 or 100%, then we got to look at how many, and like simple basic math. If you have this spinner, you've got 2 out of 6 of those opportunities for it to land on blue, right? 2 divided by 6, you got a simple math, right? That's the level of math that I'm expecting you to do in this class. You guys are all up to that, right? So if we look at a few other examples, we have probably the easiest example. You only have 2 options, heads or tails. If you were to flip this coin, ignore everything this side of here, just looking at this one right now. If you're looking at this coin, your options, how likely is it that it's going to land on heads if you flip it one time? 50%. You got, it could land on heads or it could land on tails. Those are your only 2 options. But if we're going to flip that coin multiple times and we want to see, for example, we're going to flip it, the second flip, what's the chances that we're going to get heads twice in that second flip? So you also have exactly 2 options the second time around. So you're multiplying your right here, your chances for the first one, your chances for the second one to see what the outcome would be. But if we're flipping it twice, we have that chance that it's going to be heads or tails here. And then for each of your second chances, it could be heads or tails. And so if we're looking at the possibility of outcomes, we're looking at those branches that are coming off of this, okay? So to find the probability of an outcome, we want to multiply the probabilities of its branches that are coming out of there. So with your second chance, you have 0.5 right here, 1 branch, times 0.5 chance the second time of getting the same thing. Your outcome would be 0.25. That's 1 in 4 chance that on that second flip, you end up with a heads for the first one and the second one. Okay. Some of the other possibilities, you could get a heads and a tails, or you could get a tails the first time and then heads or tails and tails as well. But those are the only possible outcomes. The more possibilities that we add in, the more possibility that we have a different outcome. So for example, if we were looking at a dice, how many sides do dice have? 6 sides. You're like, wait a second, I don't know. It's a square. It has 6 sides. And so you've got a 1 in 6 chance of it landing on any one. So you would do the same thing, just you're gonna have more branches on that tree when you work it out. So give you another example. We have a bag full of bolts. And in that bag, you have 9 good ones, 1 damaged one, but the damage is so small that it doesn't change the weight. It's just one of those threads is a little bit messed up, okay? So it's almost perfect. You wouldn't be able to tell by looking at it, touching it, picking it up by weight, anything like that. So you have an equal chance of picking the damaged one as any of the good ones when you reach into that bag. If you grab 1 bolt from that bag, what's the chance that you're going to get a damaged bolt? 1 out of, no, what's the total number you have in the bag? 1 out of 10, right? So, hold over here. You got 1 in 10 chance. So what's our probability? You can use your phones if you need to do math. 10%. What is it written as a decimal? Yeah, 0.1. Or the same thing, 1% chance that that's going to happen, right? If we take that same bag and we do this like 100 times, we put it back in, shake them up, and do it 10 different times, what would be the chances that we're going to get that damaged bolt. We multiply all that by 10. I guess I should put that, like, write it like real math people do. What's it come out at? It's still, well, not 100%. It'd be 100% if you got the damaged bolt every single time, which could happen, but it would be incredibly rare that that would happen. So if we're doing this 10 different times, you still have the same probability that that's going to happen every time. If you've got the exact same circumstances every time, you have the same chance that it's going to come out. You just have 1 out of every 10, you've got a chance that it's going to happen. So if you've got 100 times or 100 bolts total that you tried, you've still got that possibility of 1% chance that you're going to get that damaged bolt when it comes out. Okay, so the more complex the action, the greater the probability of chance or unexplained results. So the more often you do it, the more likely you get some different results. With probability, that's the number of times an event will produce a given result divided by the total number. So the math that we just worked out over here. Inference means we're predicting future behavior. And like when I just asked you, if we did this 10 more times, what would be the chance each time that you still have 1 in 10 chance, even if you do it multiple times. So we can infer that each time you have a 1% chance that that's going to happen. We don't actually have to draw bolts out every time to determine that the chances are the same if the circumstances are the same, right? So we can predict the same possible outcome. Now, in your book, they cover some other stuff and then they get to the probability. This is considered probability of failure. We pick that damaged one and we got a 1% chance of that happening. But a lot of times in safety, we want to focus more on the positive side of things. What's our possibility of success? So with success, it's going to be very simple math again that they don't cover till we're almost at the end of the chapter. So I feel like it's kind of out of place. So we're covering it now. Your chance of success equals 1 minus your probability of failure. So the probability that we just got right here. So if we're looking at the probability of getting a good bolt out of that bag, what's our chances with that one? We do 1 minus our possibility of failure. What does that equal? You can use your phones if you need. 1 minus 0. Oh, I put the wrong number here. This was your probability of failure. You got 1 in 10 chances that you're going to pull out the bad bolt. So success is going to be 1 minus the chance that you're going to get the bad one. What's the answer that you're going to get? The possibility for the good one. 0.9. Or if you looked at it here, 9 out of 10 chances of getting the good bolt. That's your chances of success, okay? So if you're talking to management about your possibilities for having injuries, you're talking about possibility of failure. If you're talking about the possibilities of success, then you want to look at that, flip it around, the opposite direction. So you've got like the 100% minus your possibility of chance says, we've got a 90% chance that we don't hurt anybody if we do this, where we got a 10% chance that we are going to hurt people. Which one is more likely to get your attention? There's only a 1% chance we're going to hurt people. Are we going to make that change? No. If it's 90% chance that we're going to not hurt somebody, are we going to make that change? Yeah, I mean, like, if you say 90% chance we're not going to get hurt, if we make the change I'm asking you to make, as management, are you going to want to make that change? Like, oh, that sounds like a great idea. So it's all about the framing, whether you're looking at possibility for failure, possibility for success, which way you want to like say it when you're talking to your management team. Okay, in the system safety process, the information is used to determine the likelihood of a system, subsystem, or component failure, and therefore it's going to greatly facilitate that decision-making process that when we're talking about those things with management, why we want them to make whatever change it is that we're recommending, we can follow it up with statistics like this and tell them probability of failure, probability of success. We can kind of emphasize why it is that we want them to change something. So if we're looking at probability of failure, we want to say if we don't make these changes, if we're showing that, we want to show that it's going to be a pretty high chance that somebody's going to get hurt. Ideally, that's what you're looking for, right? Not that people are going to get hurt, but that is going to back up that you're saying we need to change this, right? And then if you're looking at what the change looks like once we've reduced the risk, then we're wanting to report to them the possibility of success or the predicted success that we're going to see. So when we're looking at that in the kind of the thought process of what this looks like in the safety world, we're trying to prevent injuries from happening. Now, this part's not in your textbook, where the Heinrich's triangle, but this is like theory that goes back, I want to say, to like the 30s when this was first developed, and you will probably cover this in program management if you haven't already. But this goes exactly back to probability theory. From looking at statistics in place from decades of looking at accidents that have happened, they come up with this theory. Heinrich comes up with the theory that you have one serious death for about every 29 minor injuries. And for every 29 minor injuries, you have about 300 near misses and about 3,000 unsafe acts, behaviors, or conditions, right? So what do we want to focus on when we're trying to improve our working environment? We want to prevent this one fatality from happening. Where do we want to focus our work? Which one's going to be easiest for us to fix? What do you think? The minor injuries, near misses, unsafe acts and behaviors. Yeah, we have a lot of opportunity for improvement down here at this level, right? Anytime we recognize an unsafe act, an unsafe behavior, an unsafe condition, we have a chance to fix that and prevent all the rest of this from happening. Yet these are the ones that get attention, the fatalities or the major serious injuries, and even some of the minor ones if they need to go to the doctor and things like that. A lot of times there's costs associated with these where there's no costs associated with the near misses. So what that looks like in the safety world when we're trying to prevent these injuries from happening is that a lot of times we just have accident reports. That's after the fact. Those are the lagging indicators. The accidents have already happened. How do we prevent those from occurring? If we will look at those near misses and those unsafe acts and behaviors, we have a chance to go to the leading side, the proactive side, and predict possibility for outcome. It's already there for us. The statistics have already been done. We have a prediction for how likely is this to happen. So we know that we can focus our attention in this area and have a greater chance for preventing accidents and injuries in the future. When we look at probability theory, we also have to look at the population that we're evaluating. If the sample population from which the expected probability has been estimated is similar to the general to the entire population, then the statistics that come out of that are very, very, not necessarily exact, but very, very close to exact. Okay, so a lot of times what we look at in research is looking at actual people in a population. Like we're asking questions to people. We can't ask every single person in our entire population about this stuff, but we can look at a representative sample of this and get kind of everybody's point of view. One from production, one from operations, one from receiving. And we've kind of got everybody's input on this thing. Then we're very likely to address the needs of the full group of people. But if our sample population is not representative of our target population, then we have an unrepresentative sample. We're leaving out some of the important information that we need to ask about. So talking about people, that makes sense. But if we're talking about, like we've been talking about in this class, systems, we're talking about equipment, products, and services and things like that, then we need to be comparing apples to apples, oranges to oranges, not apples to oranges. We need to be looking at the circumstances and comparing the same circumstances. So we can't just look at any piece of equipment and say the likelihood of a failure is this. We have to look at the same type of equipment that we're talking about, or the same type of situations that we're talking about. What's the chances of a failure with lockout tagout? Well, that depends on one particular situation, and those circumstances always being the same if we're going to predict possibility. If we want to look at statistics, we look at what's already happened and we can see where failures have happened, but they may not be directly applicable if we have different types of equipment, different processes in place and things like that. So it's important that when we are looking at probability, we're looking at the same kind of sample that's going to be representative of the overall, whether it be people, equipment, processes, a product. We want to be looking at the same thing. Also kind of goes along with probability theory, but not really mentioned in your book, is the Swiss cheese model. And we've kind of talked about this a little bit in this class. When we're talking about probability, we're talking about the same type of circumstances over and over and over. And if we put control measures in place, we put layers of protection in place. We put guarding, we put training, we put different things like that to try to control the situation and prevent the failure. Or if we're talking about equipment, it may be things like guards and preventative maintenance, changing out parts on a regular basis, scheduled maintenance stuff going on there to try to prevent these types of failures from occurring. And the only time that incident actually occurs is when just the right circumstances all line up and allows a failure at every level. So that would be conditional probability. This reflects the chance of an expected outcome concerning the fact that the likelihood of the outcome has been influenced by certain conditions acting upon the initiating event. Meaning that when you're looking at something like flipping a coin, picking a card out of a deck, rolling a dice, things like that, the circumstances that are available are always exactly the same. When it comes to people in the work area, there's always other factors that are going to influence the possibility of what happens. And the number of control measures that we put in place and the type of control measures that we put in place makes it where there's going to be slight differences in possibilities of outcomes. So it doesn't necessarily mean that if we have a failure every single time, we're going to have an amputation. Maybe sometimes we just have a minor injury or near miss that occurs, but it wasn't quite the full-on accident because the circumstances were slightly different. So failure in a single component in a complex system doesn't necessarily mean that the total system is going to fail, because we may have redundant systems in place that are going to help to prevent that unwanted outcome. So statistics are going to evaluate a variation in that probability, the number of events, attempts to define the variation. So we're looking at all the different possibilities. So if we say, we tie this back to the working environment again, and we look at accidents, just because an accident happens doesn't necessarily mean it's always going to be the same type, right? Sometimes it might be a back injury. Sometimes it's a hand injury. Sometimes it's a head injury. There are a lot of different possibilities for what could happen. So when we're looking at probability theory, we always have to be looking at the same types of circumstances, the same situation. When we're looking at statistics, we can compare some of those differences and of the possible outcomes, the variation in outcomes that are a possibility for us. So for example, if you toss a coin, what's the chances that you're going to get a heads? You only have two options, so it's going to be what percent? 50-50, right? If the coin is tossed 10 times, you got that probability that it's going to have, that you're going to get a heads 5 out of 10 times, right? But you may not get it every time. Sometimes you're going to have those tails. So if the coin toss exercise were to occur in a groups of 10, so like each one of you flipped the coin 10 different times and you documented your outcomes, there are going to be some of you that would have 5 heads. And the bigger the group, the more likely is that you're going to have groups of people in that group, in the class that would all have, they got 5. They got 50-50 every time, right? You're going to have some that would come out with 4 heads, 6 tails, some that would be 7 and 3. So there are other possibilities. There's a chance that somebody gets heads every single time, and there's a chance that somebody gets tails every single time. So there are variations in the possibility, but you're going to see the majority of those focused around the 50-50 because you have 2 options for what the potential outcome could be. So situations where the probability of all possible outcomes of an event is known, such as that coin toss, is considered pre-assigned probability. There's no other options. There's not a whole lot of variation in that outcome. But if we're looking at possibilities where there are other considerations or there's things that are unknown, we don't have consistency in what we're looking at, then we're looking at empirical probability. So the difference would be like if we're looking at coin toss or rolling a die, we have very limited possibility for outcome. But if we're looking at this picture, what's different in the products that we're looking at here? Are all the jars the same? No, they're different shapes, they're different sizes, so the amount that's in them is going to be different. So we can't compare with pre-assigned probability and say, you got a 1 in 100 chance of picking a blue marble, one that's solid blue, out of any one of these jars. The probability is going to be a little bit different because the circumstances are a little bit different. That would be empirical probability. Okay, so the consideration of all possibilities when they're not known is going to be that empirical probability and involves statistical evaluations of possible data values. So we have to look a little bit deeper at what are all those possibilities and when are they going to present themselves. And that brings us to distribution of values, the manner in which the different values appear over the entire range of possibilities. So for example, if you're looking at this one over here, you have the numbers that are above each one of these. This is called a histogram. This is going to tell you historically what has happened when each of these things happen. This one is a compliance. So it's telling us how frequently they found compliances or failures in an inspection. Okay, this could be with a product. You could also do a chart like this for like OSHA compliance. You did an inspection and this time you found 2 failures, this time you found 6, but looking at the same work area, right? So you can see historically how frequently were your supervisors or your employees following what you're asking them to do. So we can, when we look at that, you can, with the histogram, if you were to kind of smooth out and put a line across there that shows the trends, you get what's called a curve, a distribution curve that shows you kind of on what side or where along those statistical history data that we have, where's the majority of your information coming from. So you can see over here, kind of the average that we would see is about, most of the time we have about 80%, that's where your high point is, of compliance. And that might be totally acceptable for what we're looking for. But we see that over here, we were like 40% compliance, 50% compliance. That's totally not acceptable. And so you can kind of see where presenting information visually like this with data and statistics would show a management team where, you know, if this is how often we're compliant, what was going on over here and what do we need to change so this doesn't happen, because 50% is not acceptable, 50% compliance. If we want to like over here 100% compliance, what was happening over here? Why did we get 100% compliance and how can we recreate that happening? Because right now that's really low, but we want to see more of that. So it helps us to kind of figure out where do we want to focus our attention. When we talk about variation, variance, that's the measure of variation in the observed values, or where are our statistical data historically, where are we finding it at along that line. So like if we went back to this one right here, where are we finding the statistical data, okay? And then a standard deviation is the square of that variation. Literally, you just take that number that tells you the difference in the variation. So we have a difference of like 10% from one side to the other of what's happening, and we would get the square of that, and that would tell us what standard deviation is. As far as most of the safety statistics that you do, it is very rare that you're ever going to need standard deviation unless you're doing like educational research kind of stuff. If you're putting out papers, scholarly papers and things like that, you'll need to know more about standard deviation. As far as this class and your average, what you're going to be doing when you get out into safety, more of what you're going to need is going to fall into these categories: the mean, median, and mode, the range of the data that you have, which is also going to be kind of the variation of that. And then they don't talk about outliers in your book, but it is important to take into consideration outliers. Outliers are going to be those things that are huge difference from what you normally see. Like in the sample that they have here, they have 1, 1, 3, 11, 3, and 1. 11 is way different from all the other results that you got. It's an outlier, and so it's going to kind of skew the outcome of what you got. Most of the time, what you're going to find is the normal curve, where you have kind of this section where most of your information falls right in here, and you have a little bit plus and a little bit minus. So if you have these big outliers, they can really skew your information one way or the other. So for example, if you were looking at the history of accidents within your calendar year, you might see that you're having like 2, 2, 3, 2, 4, 10, and then it going back down. That 10 is really going to skew the outcome. So it's going to make it look like your average is a lot higher than it normally is. And so those outliers say, we need to look at what happened here, but we also need to not necessarily focus all of our attention on that one thing, because it's very different from what we normally see. We need to figure out what happened there. We need to deal with that. But as far as our average plan for what we're going to deal with our everyday focus is probably not going to be what that outlier is. Okay. It may be something very different. Like we started up a new product and all of a sudden that caused a lot of issues for us. Okay. So we do need to know the difference between mean, median, and mode. And you guys probably remember hearing these back when you were in high school. And I found this little, let me turn off the light here so you can see the green one. That one doesn't show as well, that color. I found this online and I was like, that's an excellent representation of what we're talking about. So if we're talking about mean, another word for that is average. You're gonna use averages pretty frequently in industry. Like you'll report your average number of injuries. You're gonna report your average lost days at the end of every year. So you need to know how to figure averages. And an average is just mean that you're gonna take your sample, add all of the items and divide by how many of those items that you have. So let me turn this back on here for a second. So I'll write it out over here so you can actually see those numbers because I know on the pink it does not show up very well. So we've got 3 in our sample, 6, 2, 8, 2, and 3. So let's say this is, we're looking at a time frame, maybe a couple of weeks. We're looking at the average number of incidents that have happened in this time frame. What's our average here? What do? What's our first step? Add them all up. What do we get? 24. I'm cheating because I have the answers on the board. We get 24. And then we have to divide that by the whole number that we had. We got 1, 2, 3, 4, 5, 6 options. So 24 divided by 6 is 4. Our average number of incidents that we had during these weeks would be 4 incidents, right? So we would want to know if those averages are going up or down over time. That would help us to show that we're improving our program, right? Or if we're looking at compliances for our inspections, that would help us to see whether or not that's going down over time. With the mean, you're looking at the middle number. Okay, so that is just basically with all of your samples, you're looking at what number falls in the very middle. And if you have an even number of samples that you've taken, like this one, we have 6. So our middle is kind of in between this. We don't have a number that's right here. We're going to add these 2 together and divide them by 2 so that we have an average. So if we add 2 and 8 together, what do we get? 10 divided by 2. What would be our average? 5. So that would be our median. Okay, makes sense? You guys still following, tracking, doing good? Okay, now our mode is the number that we see most often in our sample. Mode most. Compare those two on each other. That's the way that I remember it. I remember like mean is average. Your median, think about a highway, but it's what runs in the middle between the 2 sides of your highway, right? And then mode sounds a lot like most. It's the thing that shows up most frequently. So if we're looking at the same sample that we have over here, we have for our 3s, we've got 2 of those. For our 2s, we've got 2 of those. 6s, we have 1, and 8, we have 1 of those as well, right? So in that particular sample, we don't have a number that occurs more often. We would have 2 modes. We would have 3 and 2 would both be modes. But if we took a different sample, like, I give you this one, the example that they have over here, we've got a 2, a 6, a 2, a 9, a 2, and a 6. Now what is our mode? The 2, because that's the number that shows up most frequent, right? Now our range is just looking at the smallest possibility and the highest possibility. So if we had numbers 1 through 10, our range would be 1 and 10. 1 is the lowest, 10 is the highest, right? And then the outliers that think one of these things is not like the other. Just kind of remember that for the outliers. It's that one thing that doesn't really fit in with the rest of them and can kind of pull your averages one way or the other. It also would pull, of course, your mean or your median as well. And so if you have some really unusual circumstances that really are not comparable to what usually happens in your work environment, you may actually want to pull out those outliers before getting your averages, your mean, median, and mode, and doing those types of evaluation. All right, and then we bring it back to the systems world. Statistical values can also be used to determine expected periods of optimal performance in the life cycle of products, systems, hardware, equipment, training programs, guarding systems that we're putting in place, whatever it might be. It can look at that. So the resulting curve that comes from that is called the product's reliability curve. And they can take a lot of different what's the word I'm looking for here? They can look a lot different depending on the product itself. So you may find that you have a consistent number of failures that happen. You always have 1 in 10 pieces that are damaged that comes out of this piece of equipment. So we'd have a very consistent, just basically a straight line. You may have some products because it's new and you're doing like research and development and that kind of stuff, that very early on you have a whole lot of failures, you make some adjustments, and then the number of failures drops off dramatically. And so you would have a curve that looks like more like this. You may have a product that starts out great. You've already eliminated these kind of drop-offs, but as the product is used, it wears out over time and at some point becomes ineffective. And so the curve goes the opposite direction with that type of stuff. And then you have some stuff that is what they call a bathtub curve, is going to be this blue one right here. And that one would be those things where early on, because it's research and development, you're going to have higher number in the beginning and then that starts dropping off. It becomes fairly consistent, but then whatever that product is also kind of wears out over time. And so then you start seeing higher failure rates the longer that thing is being used, okay? So we as safety professionals don't very often have to deal with reliability curves, but if you get to a point where you're working a lot with engineering, it is very helpful to understand what those are and what it's representing, because then you can kind of talk that same language. So the primary difference that I really want you to remember here is between statistics and probability is that probability attempts to predict occurrences of future events. We're looking forward at what could happen based on our possible outcomes. Whereas statistics is used to develop models based off of past performance, where we're looking at what has already happened. And most often in safety, we're looking to be proactive, but we can do that based off of statistics. We look at what happened last year to set up our goals for next year and predict potential outcomes and put control measures in place to make sure that we fall within those predictions. Once a probable event has occurred, it then becomes a statistic. Probable is something that's going to happen in the future. Statistic is something that has already happened. All right. Now, I only got about 10 minutes. Don't eat your homework before we get to go through these, okay? I'm going to give you guys all a worksheet, but while I'm working on passing those out, I'm going to give you a plate to put them on so I can do line these up after you're done. You put them on the plate instead of your desk, but everybody else is finished. So start separating them out by color, and then I'll give you your worksheet first. Once you get them counted out, then you're going to put yours under student number 1 on the little chart here, or how many colors you have with each color. I can math right here, right? Luckily, you guys show up for the live class. The online class will have to buy their own M&Ms for this.
Let's put on student 1.
Yeah. Or let's make so that for ease of like filling in the rest of them, 1, 2, 3, 4. So you put yours on 1, you put yours on 2, you put yours on 3, you put yours on 4, and then we'll read off what everybody else has here. guys got them sorted out? Counted? All right, let's start off over here. Number one, how many blue do you have?
17.
17. Ooh, you got a lot of blues. How many green?
10,
All right, brown,
7,
orange,
9,
red,
8,
and yellow.
5.
All right, number two. How many blues do you have?
I have 7 blues.
Right? You got gypped, huh? All right, green.
I have no greens.
No green, that's crazy. Brown,
6,
all right, orange.
18,
Wow. All right, and red,
17,
17, and yellow,
8.
8. All right, and 3. How many blues? What?
8,
8,
9,
9,
6,
6,
15,
15, 9,
8,
8. All right, and last one,
16,
16,
10,
and
4,
4,
11,
11,
10,
and
6.
6. All right. So if we look at student number one, what's your chance of getting blue? What's your total? Let's make one more column over here. Total number of M&Ms you had. That'll make it easier to do the math, okay? You can use your phone if you want to add fast. Use your fingers, whatever it takes.
Six.
56 total M&Ms. Number two.
55.
You say 50,
56.
56, all right?
55.
and
57.
57. Oh, man, you got totally gypped. They got more M&Ms than you got. So,
Mine was 56 as well.
which one was it? The
Top
first one?
one.
All right, well then, you got a bonus then. So our range of M&Ms would be 55 to 57 M&Ms in a package. And of course, the more we, if we had a huge class, like 30 students, we'd probably see a slightly bigger range. But you wouldn't want to see a huge range with something like a product like that, right? When M&Ms is putting out their product, they want to see that they have fairly good consistency in the number of M&Ms that are going into a package, because they're figuring the price of that package based off of what they're giving you for that product, right? So you'd want to see that the range is going to be pretty close. Now, as far as their consistency with getting those different colored M&Ms in the package, you can tell that they do not have a process where they dump like a certain number of blue and a certain number of red, green, etc. into that bag, because they're probably all dumped into one big pit, and then from there they get mixed up and then they get dropped into a bag. So for student number one, what is the probability that we're gonna get a blue M&M? We have 17 blue ones and 56 total M&Ms. How do we figure out the probability of that? 17 divided by 56. So what's our probability?
1, 3.
All right. 0.30. 3% chance that you're gonna get a blue M&M. What about the one that had the least? 7. 7 divided by 56.
125.
0.125. 0.125 chances of getting an M&M. So we have a lot of different probabilities here. So if we figured every one of these, right? So on your little assignment that you have, what I want you to do is figure out your probability of getting the blue M&M. Just if you pick one randomly out of your bag, which is like what we just figured right here. Just the how many blues you had divided by how many total that you had. And then I want you to add up the total of everybody in the class, how many M&Ms we had, figure out if we put them all in one big bowl and we picked out an M&M without looking, what's the chances that it would be a blue one? So what's our total number of M&Ms that we have if we add those all up? How much?
224.
224 M&Ms, and then add up all of our blue M&Ms, and how many do we have? 48 M&Ms. So 48 divided by 224, that's gonna tell you the chance that you would end up with a blue M&M if we just dumped everybody's M&Ms all into one, right? Then the only other thing you have to do on this, you got one more question on the front of your sheet, two more on the back. What I want you to do is for your own, or for the group total, to make sure you wrote all these numbers down, for your group total, what's the mean, median, and mode for each color of M&M? Okay, so the first one is you're gonna write the mean for blue, the mean for green, mean for brown, etc., right? So remember, when you're writing that down, you're gonna need like this number, this number, this number, and this number for the group. Like when you're doing if you're doing the average, we're gonna add those all up. We got 48 divided by how many? 4. The average is gonna be how many M&Ms? 48 divided by 4, what's that? 12. So your mean of blue would be 12 M&Ms. Nobody got 12 M&Ms, but that's telling you what the average would be if you had a larger sample. And you were going off of the data that we collected here, right? So you're gonna do the same thing for the other colors, okay? Now for the median, we have an even number, so what do we have to do here? Add these two together and divide them by 2. 7 plus 8 divided by 2. You're probably gonna come up with 7.5, is that? So 7.5 would be your median for the blue M&Ms. And then your mode, you don't have one that's most frequent, so NA, you don't have a mode for that one. You have exactly the same number. If we had a huge sample, we'd probably find a mode for that one, but since we only have 4, we don't really have a mode. And it's time for me to let you go, so make sure you guys have the number that everybody had of each color, and then you can finish this and bring it back to me next week. Because I haven't put it in in Canvas yet for you to upload things, so you just bring them back on Monday and give them back. And you get to take your M&Ms and now you may eat them. You're like, oh, I already did. See, statistics wasn't that scary, was it? Now, when you get into using statistical software, it's scarier. But I won't make you do that. You get into the master's program, then you might get to that level. But at this level, I just want you to know basic everyday stuff you need. All right, you guys are pretty cool.